So next, near 1868, Mendeleev and Lothar Meyer, so these two renowned scientists, Mendeleev and Lothar Meyer, so they independently noticed the properties of elements are periodic functions of their atomic weight. And then they independently tried to come up with their periodic table. But Mendeleev got most of the credit, and in 1871, Mendeleev published his short periodic table. So this one is the original Mendeleev's periodic table. And till that time, only a few elements were known. And all these 118 elements that we know now, it was not known at that time. Now let's learn about important things on Mendeleev's periodic table. So in Mendeleev's periodic table, it was 7 periods and 9 groups. If you see here, so these rows are called periods, these rows, and these columns, they are called groups. So in Mendeleev's periodic table, there were 7 periods and 9 groups. So in first period, only 2 elements were there, and that is called very short period. So in the second and third period, 8 elements were there in each, and these were called short period. In fourth and fifth period, 18 elements were kept, and those were called long period. And in sixth and seventh period, 32 elements were kept in each periods. So these are called very long period. Now each long period is divided into even and odd series. Zeroth group contains inert gases, though it was absent in the original Mendeleev's periodic table. So at that time, right now, the inert gases are in group 18, but at that time it was called zeroth group. Now group 8 contains 3 elements of close atomic weights in one place. For example, iron, cobalt, nickel, and ruthenium, rhodium, palladium. These three elements were housed in the group 8. For example, you see here, iron, cobalt, nickel, they are kept in group 8, and ruthenium, rhodium, palladium, they are also kept in group 8. You can see osmium, iridium, platinum, they are also kept in group 8. Now correction of atomic weights were done, and so that Mendeleev became successful to determine the correct atomic weight in some cases. For example, beryllium and indium. So that time when they were doing this research, that time there was some issue with the correct measurement or precise measurement of atomic weights. So when he was putting these elements, so in his chart, so that time while when they saw that chemical nature or the physical natures are matching, so in that respect he can put beryllium in this position, and also he can put indium in the respective position, and in that way it was automatically they could assume the atomic weight of this beryllium and indium. So the correction was done by Mendeleev. Now prediction of missing elements. So at that time of Mendeleev, they had only 63 elements known. Now to maintain the order of atomic weight, he had kept some vacancies, so which inspired the discovery of new elements. For example, scandium, gallium, germanium, technetium. So all these elements were not known at that time. So he kept vacancies, and in that vacancy, people assume that yes, some other atom can be there. So that inspired to find out more and more atoms. Now this is the modern version of Mendeleev's periodic table. Next, we will do the comparison of the properties of group 1A and 1B. So for that, you can see, so this group 1As are called alkali metals, and that time group 1B were called coinage metals. So you can see the outermost electronic configuration is NS1, and here N-1 D10 and NS1. So valency, group 1A elements had valency 1, whereas this group 1B metals, they had different valencies. For example, copper had 1, 2, sometimes 3, silver had 1, sometimes 2 and 3, gold also had 1 and 3. Now if you compare the state of occurrence in nature, so this group 1 elements, they exist in compounds and never exist in free state, whereas group 1B, they exist both in chemical compounds and free state. Now if you compare the electropositive character and reactivity, so group 1 elements, they are highly electropositive in character and highly reactive, whereas group 1B elements, they are less electropositive in character, and the decreased activity makes them noble metals. If you see the bonding nature, so group 1 elements used to form ionic bonding, whereas group 1B elements, due to the higher polarizing power, they introduce more covalency in their bonds. Now nature of oxide and hydroxide. This group 1a elements is to form highly alkaline materials, whereas these group 1b, they form slightly alkaline compounds. Now, if you see complex compound, so in case of group 1a, no marked tendency is noticed to form coordination compounds. Only some complexes with the oxygen donor are reported. And in case of 1b, a marked tendency to form coordination complexes is noticed due to the ligand field stabilization energy, except for +1 oxidation state. So these things, these electronic configurations or ligand field stabilizing energy, these things I'll discuss later in some other chapters. So for the time being, you can try to understand what are the differences between this group 1a and 1b compounds. Now, if you see the color of the compounds, so group 1a elements, they generally form colorless compounds because of the absence of ligand field band, that is DT transition, and charge transfer band, metal to ligand or ligand to metal charge transfer. Now, in case of group 1b, those compounds are generally form colored compounds due to the presence, those molecules. So they generally form colored compounds due to the presence of the ligand field band and charge transfer band. Now, if you see that hard-soft principle, from there you can see this group 1a elements, they are hard acids, whereas this group 1b elements, they form soft and borderline acids. Now, if you see the structure of metallic crystals, group 1a elements, they adopt the BCC, body-centered cubic structure, and possesses low cohesive energy, giving rise to low melting points and density. Whereas this group 1b elements, they adopt the FCC structure and are highly malleable with a higher cohesive energy, higher melting point, and higher density. So these things you can take a note if you need. So we have discussed about the importance of Mendeleev's periodic table. Now we are going to discuss the defects in the Mendeleev's periodic table. So each coin has its two sides, right? So for example, the reverse atomic weight order in some cases were observed in Mendeleev's periodic table. Though the elements are placed in the order of their increasing atomic weights, in some cases the trend is reversed. So there are 4 such pairs. So you see iodine and tellurium. So iodine had lower atomic weight compared to tellurium, but iodine was placed before tellurium. Similar to that, potassium and argon. Potassium had low atomic weight, but it was placed before argon. Nickel had the lower atomic weight compared to cobalt, but it was placed before cobalt. Now, next defect was triads in group 8. So in group 8, there were 3 elements which were sharing that space, right? So though the different elements are separately housed in different rooms, in group 8, the 3 elements, that is iron, cobalt, nickel, and in the next period it was ruthenium, rhodium, palladium, and in the other period it was osmium, iridium, platinum. Those were placed in each of the single rooms of the period 4 to 6. The members in each triad are not similar in terms of properties, but still, because of the absence of suitable vacant rooms, they were placed in the single rooms. Now, the next one is subgroup elements lacking in similarities. So each group was subdivided into A and B subgroups. But in the long periods, similarity in the properties of the two subgroups is hardly found. For example, the alkali and coinage metals are widely different in properties, as I have shown in the previous slides. That comparison of 1A and this one, comparison of 1A and 1B elements. So they are kept close to each other, but they have completely different properties. Next one is the positions of isotopes and isobars. So according to the placement in the order of atomic weight, the isotopes should have different positions, while the isobars, so this isotope means you have, so if you see the isotope, that means you have same number of proton but different number of electron. So that means your atomic weight will be different. And isobars means you have different number of protons but same number of total atomic weight. Means atoms of the different elements, but the atomic weight is same. So the both proton and neutrons might be different, but their summation, the atomic weight, will be same. Those are called isobars. So these isobars should be placed in the same room. So this was not justified in Mendeleev's periodic table. Next was group valency. So though the group number indicates the highest possible valency state, that is, in case of oxygen valency, it might be 8 of the elements, except ruthenium and osmium of group 8. No one in the group shows the valency 8. So if you see, so the highest possible valency was denoted from the group number, but in reality, they don't show that much of valency. Now missing link between the group 7b and group 1a elements. So transition from the highly electronegative halogens to the highly electropositive alkali metals through the inert gases can hardly be rationalized in terms of atomic weights. Next one was the relative stabilities of oxidation states. So the relative stabilities of the different oxidation states of an element cannot be interpreted from its group position and atomic weight. Means the stability of the oxidation states you cannot predict from this Mendeleev's periodic table. Peculiarity of the lightest congener in each group. So the first member of each group is drastically different from the other members of the group. For example, if you see the periodic table, you see helium, neon, argon, krypton, or this hydrogen, lithium, sodium, potassium. So in this group, the hydrogen has drastically or dramatically different properties compared to the other elements. Similarly here, in case of beryllium or boron or carbon, so they have different properties compared to rest of the elements in this group. Next was the diagonal relationship. So the existence of diagonal relationship for the short period elements can hardly be rationalized in terms of atomic weights. So this diagonal relationship we will explain in later lectures. Position of lanthanides and actinides. The position of lanthanides or actinides in a single room cannot be properly understood in the Mendeleev's periodic table. The next one is uncertainty in the prediction of the number of missing elements. So the successive members in the periods differ in atomic weights by different extents, that is 1 to 4 units. Hence, it is difficult to predict the number of missing elements present between the elements whose atomic weights are known. Because of the fact it was difficult to predict the exact number of lanthanides and actinides from the knowledge of atomic weights. So if you know two elements and that has higher atomic weight gaps, so you cannot predict that how many more elements will fit in between those two elements, right? The next one is the position of hydrogen. That was also arbitrary. Now the position of hydrogen creates a confusion as it has similarities in properties with both the group 1, that is alkali metals, and group 7b, that is halogen elements. Now different capacities of the periods. So the different capacities, that is in first period it was 2, in the second and third it was 8, then fourth and fifth it was 18, and then sixth and seventh it was 32. So the different capacities of the different periods to house the elements cannot be rationalized from the Mendeleev's periodic law.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.